Right. Welcome to our waves unit. We've spent the first part of this year learning about particles. No matter whether we were talking about electricity or mechanics, we were talking about actual objects that you can see and hold, such as like this golf ball right here, okay? This is a particle. They can move from place to place, and the main thing about a particle, at least for our purposes right now, is that they can carry energy with them, okay? They can carry energy from place to place. There is a whole other class of things that exists out there that you are very familiar with, but that we have not talked about this year, and that would be waves. A wave transports energy just like a particle does, but it does not transfer matter. Remember, matter is just stuff, okay? So if this golf ball brings energy from one spot to the next, it also brought all that matter with it. A wave, on the other hand, can transport energy without any net transfer of matter. Objects that allow the wave to happen, they can move, but they'll always end up coming back to their starting positions, no closer than they were before the wave has passed. So waves do not transfer matter, they transfer strictly energy. Definition of a wave is a vibration that moves through a medium. Medium is just a fancy word for some type of material or matter. Type of material. Okay? Or, if a wave does not move through some type of material or matter, it can move through what is known as a field, like an electric field or a magnetic field. Waves are created, no matter how they move, what they move through, they are created by a particle vibrating or oscillating. Oscillating is just a fancy word for back and forth movement. So moving back and forth around some average position. And there are really two types of waves that we are going to talk about in this class. The two types of waves that we are going to talk about are longitudinal waves and transverse waves. We're going to talk about longitudinal waves first. Longitudinal waves are waves in which the vibration is parallel to the direction of motion. Let me show you a quick picture of hold on a sec. All longitudinal waves need some medium, some material through which to move. In other words, longitudinal waves cannot propagate, which is just a fancy word for move. They cannot happen through a vacuum. Vacuum, if you remember, is just empty space with no material in it, no matter in it. This is why, for instance, sound waves are longitudinal waves. You cannot hear things in space because space is an empty vacuum. There is no particle out in space, okay? There's not air in space. There's nothing. And because there's nothing out there in space, then think about how sound waves work. They work because of pressure variations in the air. When you talk, your vocal cords are creating waves, areas of higher pressure and lower pressure, that move out from your mouth and into the air around you. Someone else hears that, and they register those variations in pressure with their ear, and their brain interprets that into sound. In space, if there's no air, then those pressure variations cannot be created in the first place, therefore sound does not work in a vacuum. Okay? Longitudinal waves cannot propagate in a vacuum. Another name for waves that actually require a medium, require a material to move through, is mechanical wave. You might hear that term a few times. I'm going to show you a couple clips of longitudinal waves. Here's a nice longitudinal wave for us. Notice that it seems like something is moving to the right, from left to right, okay? But if you look at the individual particles, like look at this red one right here, it is simply moving back and forth about around my cursor here, okay? We even have arrows down in this picture, it's really the same picture pretty much, that show that these particles are just moving back and forth. The particles are not moving to the right from the left. What's actually happening is the compression area of those particles is moving, okay? There's a pattern that moves. So look at this right here. It kind of brings in particles, they get denser for an instant, and then they move back to an area where they're less dense. But that density pattern is what actually moves. Really interesting. Okay, so we see down here, we have wave and particle. Particle moves back and forth, but the wave moves all the way through. And then we have some nice names down here that you might want to know. These spaces where there's a big density of particles, we have compression is where there's a density. Rarefaction is where there is basically a low density of those particles. So here's a really good video or animation of a longitudinal wave. And again, notice the waves are moving left to right, the particles are vibrating left to right, parallel to it. Here's another video, and I've got this slowed down, of a longitudinal wave on a slinky. Now watch this little piece of string right here, or whatever this is. When I play this little piece of string, this little blue thing, is going to oscillate. The person is going to cause longitudinal waves to happen by pulsing their hand back and forth. But this little piece of string, it doesn't move any farther down the slinky. Okay, it's tied to the slinky. It doesn't move any farther down. It always returns to about the same spot. Okay, so you can see I've got I had my cursor there. It's moving basically. All right, so let's see. It's moving basically right around the cursor. Okay, it goes farther away and then it comes back. Let's move it back a little bit. There we go. I don't know how I got this off-centered with it. Now I'm too far off-center. There we go. But anyways, see how it just oscillates about this point, okay? It never actually moves away. It does move side to side, but it always returns to approximately that point where my cursor is, okay? Anyways, that's enough of that. That's what a longitudinal wave does. Notice that the matter, it moves temporarily, but it always comes back to the same spot. We're going to draw a picture of a slinky undergoing compression and elongation. Another word for rarefaction would be elongation. I think that's a little bit better for you guys to know. Undergoing compression and elongation waves. So here's how we're going to draw this. We're going to draw a slinky. We're going to draw an area of compression right here. Then an area where the slinky is more spread out. Another area of compression. Now the slinky spread out. Compression. Slinky spread out, compression, and so on and so forth. We have compression at these locations, and elongation in between. Okay? If we were to look at just one little piece of this slinky, like say for example we take a look at this little coil right here, we would say that the piece of the slinky, that coil, it moves back and forth parallel to the wave direction. And as a matter of fact, I forgot to put this in. The wave is traveling in, let's say, this direction. Okay, that piece of slinky is not going to end up farther down when the waves stop moving. It's going to end up exactly where it is. It might get pushed this way initially, but it's going to come back. Okay, it might get pulled this way initially, but it's going to come back to its original position. That's what a wave does. It doesn't necessarily move matter permanently. It simply transmits energy without any net motion of the matter. We could get into why the slinky moves in the first place. It has to do with some spring forces here, just like pressure waves have to do with air particles kind of making areas of high density and then areas of low density, but that's not super necessary for what we're doing. We just care that the matter doesn't end up moving permanently. So other examples of longitudinal waves, and instead of just this slinky one, are sound waves. Those are the biggest type of longitudinal waves that we're going to focus on. And actually P waves from earthquakes, if you remember your earth science. P waves are one type of earthquake wave. The second type of wave we're going to talk about are transverse waves. If longitudinal waves were waves in which the vibration of the material was perpendicular to the direction of wave travel, transverse waves are the opposite. Or excuse me, parallel to the direction of wave travel, transverse waves are opposite. Transverse waves are waves in which the vibration is perpendicular to the direction of wave travel. These are different from longitudinal waves because even though some transverse waves can propagate using a medium, there are some types of waves that can actually move through a vacuum, and every single one of those types of waves is a transverse wave. These particular transverse waves can move through a vacuum because they don't vibrate in matter, they vibrate a field. And what that really means, how do you vibrate like an electric field? It means that the strength of the electric field is changing in a repeatable pattern. Let me give you a couple pictures of what a transverse wave looks like. I'm going to zoom this in. So I'm going to, let's see, we're going to hide the green wave and hide the orange wave. And you see that we have just a bunch of dots on here, basically. If I do slow motion, what's going to happen? Oh, let's turn up the frequency. Okay, there we go. Do I want wave speed up? Yeah, fine. Okay, so if you notice, it looks like we have what's known as a transverse wave. You can see that the wave is moving from left to right. Okay? If I do slow motion, though, let's look at the individual little dashes that are causing this wave. Let's look at this one right here. Okay? Notice as it goes up, and then it goes back down, and it stays on that line the entire time. Okay? That's really interesting. While that piece stays right on that line, the wave itself, the disturbance, moves left to right. So we see that the wave is moving left to right, but the individual pieces are moving up and down perpendicular to the direction of wave travel. That is a transverse wave. Okay. You can also have a transverse wave on a slinky, just like this. Notice that the slinky, the wave is coming towards the camera, but the slinky, the coils themselves, are vibrating kind of in that left-right direction. Again, perpendicular. Okay, I think they're going to do it one more time. Yep, left-right motion. The wave, however, comes towards and away from us. Okay. So here's an example of a transverse wave. A slinky that waves side to side. And we will get out the slinkies and demonstrate this in class. So you got a nice sine curve wave looking thing here. So the slinky's getting shaken back and forth side to side. Imagine this is like a top-down view of it. The wave is traveling, let's say, in this direction. This little piece of the slinky right here does not move with the wave travel, okay? It doesn't ultimately end up farther along the direction of wave travel. It's simply moving, from our perspective, up and down. This piece of the wave moves up and down, perpendicular to the direction of wave travel. Okay. Earthquake S waves are also transverse waves in addition to some types of slinky waves. So notice a slinky can do both. You can do longitudinal waves with a slinky. You can also do transverse waves with a slinky. Earthquake S waves are also trans waves. The most important type of transverse wave is an electromagnetic wave. These are also known as light waves. Light is actually a wave. Really quick, we got to talk about different types of waves in terms of what they look like or how they repeat. I'll keep it here first. Okay, if you ever hear a wave pulse, this is a single short disturbance or vibration, a single vibration of a matter or field. Okay, so if you just sent, like when we were watching the longitudinal video and the person's hand was going one push, and then it would wait, and then another push. Those were pulses. Pulses can be either transverse or longitudinal, and they travel in one direction. If you repeat the pulses at a regular interval, then what is known as a periodic wave is produced. Periodic means it has a certain period. It repeats after some period. So let me just show you a little simulation that I have. Okay, this would be a periodic wave if we had something that was continuous like this. A pulse, on the other hand, is going to look like this. I control exactly when this happens. Okay, it's single short disturbance. That's a pulse. This, on the other hand, would be a periodic wave. Okay, pulses can have their shapes vary, such as that pulse is really tall, this one is a lot shorter. Here's a wider pulse. Okay, so pulses can have all sorts of different shapes to them. Let's draw a few in. All the following would be considered pulses. Everything you just saw, by the way, is those are transverse wave pulses. So there's a pulse. You could have like a kind of square-looking pulse. You could have a triangular-looking pulse, like we just had. All those are pulses. Transverse waves. Wave pulses on a string. Now, you can have longitudinal pulses as well. Those are a little trickier to draw. A longitudinal pulse, here's how I'm going to do it. Remember how we kind of saw that there was like little disturbances in that one clip as the dots moved back and forth as longitudinal waves, but the density clumps kind of moved left to right. We're going to kind of show something sort of like that here. What I'm drawing are called wave fronts. I'll explain them more in a future video. These are all wave fronts, and then a pulse might look something like this. Those wave fronts have all gotten much closer together, but there's only, one set of those clumps. Otherwise, it just continues for indefinitely. Okay, that would be a sound wave pulse. And remember, sound waves are longitudinal. Now, interestingly, and we'll get to this, we'll talk about this more in the next few videos, the speed of a pulse or a periodic wave depends on the medium it is in. So the material. Some materials or mediums allow pulses and waves to move faster than others. So for example, light actually moves much, much faster in air than it does in water. Sound is actually the opposite. Sound moves faster in water than it does in air, interestingly enough. We'll get to that later though, but that's a good fact that you need to know. When you have a pulse or a wave and it encounters a different medium, a different material, three things happen. Okay, there's three options. Part of the wave is going to be transmitted. In other words, it's going to go across into the different medium. You can think of it being like a barrier, a boundary between the medium, between the two materials. So part of the wave is going to go across that boundary. Part of the wave is going to be absorbed. So whereas the wave had some wave energy beforehand, whether it was kinetic energy or some sort of potential energy, at the boundary, some of that energy is going to get transformed into something else. So the wave actually loses some energy. And then finally, part of the wave is going to be reflected, meaning bounced back from the boundary. So three things can happen. Part of the wave is going to go through, part of it's going to be absorbed, part of it's going to be reflected. We have actually all of those things happening right here in this picture. This is light. This is laser light that is hitting a prism. There's red and green laser light. We don't have to look at both, but you can see here's where the laser light is coming from, off to the right here. It's traveling in air, and then it hits this prism. This prism is the new material. It's the new medium, and the spot where it hits, where we transition from air to glass, is the boundary. So this is the incoming wave. You can see that part of the wave, let's just look at the red one, is transmitted. Part of it goes into the new boundary. Part of it's reflected. There's this little kind of darker line down here, not as much light. And I bet if you were to add this red light to this kind of darker, or this transmitted light to this dimmer red light wave, they would not equal the total light, the total brightness, you might say, of this incoming wave. So we see very clearly here the transmission and reflection, and I'm betting there's also some absorption. Okay, so we have to know what those things mean. Let me draw another example of this for you. Let's say that you have a wave, let's say you have a string, and a string that's tied to a thicker string. So we're going to have two spots. We're going to have a boundary between these two things. We're going to have a wave on a thin string. It's like a little tiny rope, and that's going to be tied to a wave on a thicker string. Okay, so there's our thin string, and then here is our thick string. Notice we have a wave coming in like this. The wave on our thick string I'm going to draw like this. Of course, my artistic skills are letting me down a little bit. Hopefully you can tell that this is thicker. And I want this to, we're going to bring this up a little bit, we're going to bring this down a little bit. Okay? What I want you to notice is that as the wave goes through this boundary, it gets tied and hits the thicker string. I'm going to make this look even thicker here. You'll notice that it's still moving, but it seems to have lost some of its, I guess, height, the height of these peaks here, these crests. So what we're seeing is some of the energy, it just doesn't have enough energy to cause the big changes, the big crests and the big troughs at these low parts. So it seems to have lost some energy. Some of that energy was transmitted, and what you also might see in certain cases is some of that energy being actually reflected back. Like so. Okay, so what happens, and that's reflected back this way, at the boundary, some energy is transmitted, some is absorbed, and some is reflected back. And what you might notice, and we're going to see another demonstration of this in just a little bit, is that at the boundary, some of the reflected part of the pulsar wave may be inverted. In other words, it flips upside down if it meets what is known as a fixed boundary, like a wall, something that can't move. We don't have to get into the mechanics of why it inverts, we just need to know that it does. Let me show you an example of this. Okay, we're going to change this to a fixed end. And we're going to put a pulse, we're going to send a pulse through. Notice how it inverts, and then this is a fixed boundary as well. Notice it inverts at the fixed boundary. Okay? That's what happens to a pulse or a wave when it hits a boundary that is fixed and can't move, it inverts. If instead it happens at a loose end, something like this, notice that there's a little ring that can move. It does not invert, but that's still a fixed boundary, so that inverts. Okay. Again, there's some mechanics as to why this happens. It has to do with forces and Newton's third law. We're not really going to get into it this year. It's just enough for you to know what happens at a fixed and a loose end. So let's draw these out real quick. Here's a wave coming in. And again, we will demonstrate all these in class as well, but good to see the demonstrations for right now. It hits a wall, which is fixed. When it bounces back, nothing else has changed, but it bounces back inverted. If the pulsar wave encounters a boundary that can move, the wave is reflected right side up, the way it came. So this is a movable boundary. And it goes back, right side up. The last thing that I want to talk about is a question that comes up on the homework a lot. When you're looking at a wave, it's really important to be able to tell what's going to happen to the piece of the medium that is about to undergo changes because of the wave. Okay? It depends on the type of wave and the direction that that wave is traveling in. Okay, so what I'm going to do here is, let's see. All right, So we're just going to do slow motion for a second. All right, we're going to do another pulse. So notice, we've got this wave going here, and I want you to think about what's going to happen to this little green particle. As this wave shape moves, what's going to happen right here? Well, this trough is going to get there first, so I would bet that the green particle is going to go down first, and then as the crest comes by, it's probably going to go up. So I'm thinking down first, then up. And that is exactly what happens. Down first, then it goes up. Okay, and again, down first, then it goes up. This time it's going to go up, then it goes down. So, the direction the wave is traveling and the shape of the wave are both important for this. If we were to draw out an example of this, it might look something like the following. Okay, here's the wave, here's point A, wave is traveling this way. As the wave passes point A, it will move down first, then up, then back down. In other words, this trough will hit A first, which means A must go down. Okay? Think of it as like A is almost getting pulled down because these pieces of the wave are they're causing a force on A. They're going to pull it down. Then these pieces are going to pull A back up, and then it's going to return to its normal spot. If we can even do this for something a little more complicated. A wave maybe looks like this. Okay, let's say that this is B. The wave is traveling in this direction. As these parts of the wave get to B, B must ride up to go along with them. Then it'll go down, and then it'll return to normal. So as wave passes, B moves up, then down, then up. Okay, there's a really basic introduction to waves, just their general features and how they work. Our next video will be on the different characteristics of waves and what we can measure for individual waves.